Here we still talk about functional groups. We have carbonyl derivatives, carbonyl-containing compounds, carbonyl-containing molecules. Also turns out when we actually we're going to talk about probably in organic chem too, as far as the oxidation products of alcohols. One of the oxidation products of alcohols will form a carbonyl-containing molecule. The carbonyl group is the C double bond O group. Carbonyl group. All of the molecules we actually going to show, as far as at least the carbonyl-containing molecules, all of them are going to have a C double bond O group, a carbon double bond into oxygen. If you have a hydrogen directly attached to this carbonyl carbon, this molecule is referred to as an aldehyde. Hide, kind of like hydrogen. Hide. It's an aldehyde. Another molecule for carbonyl-containing group. In the second molecule, we got the carbonyl-containing. We have the carbonyl carbon or carbonyl group. Attached to the carbonyl carbon is going to be two carbons. When you have two carbons directly attached to the carbonyl carbon, that is considered to be two single bonded carbons. This molecule is considered to be a ketone. Also, we have like a little molecule called the aldehyde. When we took like the H of an alcohol and convert it into a carbon, in this case, we're going to take the H out of the aldehyde and convert it to an OH, to oxygen. This group here will see we kind of have like two different type of functional groups. You got the OH group from like an alcohol, and you also got a carbonyl carbon. So it's kind of like there's two groups, you actually have two names. This is called a carboxylic acid. And one component is formed like when it's different with a single bonded group, there'll be like an alcohol and another group together, kind of like two names. This little group together also has like two names, carboxylic acid. Put both names as far as naming it. Not equal as far as like doing a particular group. When we took one group, we actually converted the H into a C as far as like the derivative of water. We're going to convert the H of the carboxylic acid into a C. Once I convert the H into a C, I'm given the name of an ester. I had a student years ago, and they were trying to find ways how to end up distinguishing between an ether and an ester. Esters like two eggs, like Easter egg, Easter honey. So eggs, two O's is an ester. Also, we can convert our oxygen atom into a sulfur. Remember yesterday we said if we have a sulfur atom, how do we indicate that we have a sulfur atom present in a molecule? For example, we did an alcohol. We convert the OH of an alcohol into a sulfur. And we had a word that actually let us know we had a sulfur atom present. What word do we use? Thigh. If this molecule was an oxygen atom, it would be an ester. If I replace my oxygen atom with a sulfur, what name do you think we call it? Thioester. Anytime you see thigh, that refers to a sulfur atom. You see a molecule with thigh and stuff in it, another molecule somewhere going to have a sulfur atom. Also in the form, we converted our oxygen atom into a sulfur. We also converted the oxygen atom into a group 5 element. For example, converted to a nitrogen. Now, organic chemistry, there's a different name for it. Now, biology majors also have a different name for the molecule, for that particular linkage. Any biology majors? Look at the biology majors. So what name is given to the linkage right here? You focus on it. What type of linkage is that? Not for biology majors. What y'all talking about? Now, or chemistry, we have like a different name for, but biology majors, y'all call it biology. Start with a P. Start with a P, a linkage. Don't go up here. Come back a little bit. Phosphate have a phosphorus. There's no phosphorus in the molecule. Has a linkage, start with a P. Say again. Take the poly off. Poly just means many. Peptide. Peptide linkage. Anybody made heard of peptide before? The little name peptide. Put y'all on the spot and put like I try to fold like a deck of cards. But again, you call a peptide organic chemistry referred to as a amide. Now, if you want to call a peptide or amide, and obviously since we have a lot of biology major, I'm not mad about you call it peptide or amide. Just you need to know that a peptide and amide are based on the same things. Also, we converted to a group 5 element. We also remember converted into a group 7 element. Where X is equal to fluorine, chlorine, bromine, iodine. Now, as far as what the X group equal to, the most common one that X equal to is actually chlorine. Bromine, probably second, but bromine is like a distant second. Iodine and fluorine, very seldom I've seen an iodine and fluorine before even used. As far as naming this group, this molecule was derived from a carboxylic acid. This will be an acid X. What did X refer to? We already said it in the halide. So those would be an acid halide. Do we have a little X in group that we said last time as far as like an alkyl halide? So guess we're not trying to reinvent the wheel every time we define something. All we try to do is tweak a little bit of stuff here as far as different names of it. And also you can have it what you have 2 carboxylic acids. You're going to circle out water, H2O, and combine what's left. The molecule I just drew the board was derived from what? To what?
Carboxylic acid.
So we got the acid. And we removed what from it? Don't you remove it? You go on up here again. What we remove from it? Water, H2O. Right? This supposed to stop going up here. We got removed 2 hydrogens and 1 oxygen. That's H2O. When it basically the loss of, AN is like basically referred to the loss of hydride, loss of water. So it's going to be an acid and hydride. And again, also again, we could cover a whole bunch of different more little functional type groups. Again, like I said, what I don't like to try to do is actually try to give you like and try to bombard you with so much detail and stuff, and your brain kind of goes like boom, blow up or something like that. We're going to stop with that particular list, and again, I will point out there's a bunch more. In fact, when we get into organic chem 2, we're going to talk about a bunch. We're going to talk about names like acetal, ketal, hemiacetal, hemiketals. We're going to talk about cyanohydrin, amine, enamines, beta hydroxy, beta keto acid, etc. type names, stuff like that. But again, we're just going to stop. These are the lists as far as the functions we're going to deal with. And if we on exam numero dos, I may ask you as far as to identify a functional group, or it could ask you here, draw me a generic aldehyde, draw me a generic ketone, draw me a generic carboxylic acid, or draw me an amine, etc. type group. Does everyone have the aldehyde, ketone, carboxylic acid listed already? Now we have a little bit more fun. And we're going to talk about far as degree types. Determining degree types. We're going to try to determine the degree type of alcohol that we have. And when the degree type one, we're not going to go too much different what we already talked about as far as doing degree types. As far as determining the degree type of alcohol, for alcohol, first thing we'll look for is what? We'll look for what group for alcohols? The OH. The first thing we do is locate our OH. Find the OH. Find the carbon the OH is directly attached to. How many carbons is that carbon atom directly attached to? Make sure I see the numbers. Start with let me put A, B, C, D. A, B, C. Doing molecule A. How many carbons is the carbon with the OH attached to?
1.
Is it 1, 2, 3? Can I get two for numbers? 3. On this is A. I'm finding my OH group. I'm finding my carbon the OH group attached to, which is this carbon atom right here. How many carbons are directly attached to that carbon atom? 3. Everybody see a 3? I want to have the class someone like 2, 7, start like they're doing playing football or something. Call a whole bunch of different crazy numbers. This here will be a 3-degree alcohol. If I look at molecule B, we're going to determine what type of degree alcohol is molecule B. Again, we do the same process. Find my OH group. Find the carbon the OH group attached to, which is the carbon we'll put a star next to. How many carbons are directly attached to carbon atoms? 2. That will be a what degree alcohol?
2 degree.
2 degree. Not too high, right? Go into molecule C. What degree alcohol? Again, we do our same steps. First thing we're going to do is locate our OH group. We're going to find the carbon the OH group is attached to. It's this carbon atom. How many carbons are directly attached to the start carbon? There will be a what degree alcohol?
1 degree.
1 degree. COH. Well, same thing. We're going to find the OH group. We're going to find a carbon that the OH group attached to.
Zero.
We're going to put a star beside that carbon atom. How many carbons is that carbon atom directly attached to?
0.
0. There will be a what degree alcohol?
0 degree.
0 degree alcohol. You probably think something super hard and crazy, weren't you? 0 degree alcohol. Now it turns out for all of the degree type alcohols, only one alcohol has a name, which is set to it, and that's the 0 degree alcohol. What name is given to the 0 degree alcohol? How many carbon atoms make up a 0 degree alcohol? 1. What name goes with 1? Methyl. Same thing with the same little number we did earlier. It's not changing. Ain't gonna change like, oh, he said methyl for exam 1, for exam 2 gonna be a different name, different number. No, same name as far as 1 carbon atom was met. It's still the same 1 carbon atom which is met. You can do it 2 ways. You call this methane. Since it is an alcohol, you drop the E and add OL. Or you can name it as far as call the parent name as being alcohol. If the parent name is being alcohol, because we call the parent name alcohol, we're going to call the 1 carbon atom group to be a substituent. 1 carbon atom substituent is called methyl. And we use the parent name as alcohol. You can also refer to as methyl alcohol. Wasn't that funny? But not too hard, right? Now we're also going to look at as far as alkyl halides. Now we're also going to do a similar thing with determining the degree of alkyl halide. What degree alkyl halide do we have? We put a little A, B, C, D. A, B, C, D. What degree? First, now for alkyl halide, the first thing we're going to focus on is going to be the what? Remember, alkyl halides, first thing we're going to focus on is going to be the with group 7. So the halides. What are the halides? Fluorine, chlorine, bromine, iodine. Those same 4 ain't going to change. It didn't change from G-Chem to organic. It's still the same 4. Fluorine, chlorine, bromine, iodine. So the first thing we do is going to identify either the fluorine, chlorine, bromine, iodine in molecule A. Which halide are we referring to? I want you to say it. Bromine. The reason I want you to say it is because you say it, you might start believing it. I was like, yeah, I think it is, but I'm not really sure I want to say nothing. I think you say it, you start believing it, and you start flowing with the stuff. So the first thing we do is form our bromine. We're going to find the carbon that the bromine is directly attached to. How many carbon atoms? We're going to put a star beside the carbon atom bromine is attached to. How many carbon atoms directly attached to the carbon atom? 0. There will be a 0 degree alkyl halide. Looking at B. For B, first thing we're going to do is identify the halide. In this case, the halide is going to be iodine. We're going to find the halide. Find the carbon the halide is directly attached to, which is this carbon atom. How many carbon atoms directly attached to the starred carbon atom? That would be a 3 degree alkyl halide. Looking at molecule C. Again, first thing you look for is the halide. In this case, the halide will be fluorine. We're going to find the fluorine atom. Find the carbon directly attached to fluorine. Where you put a star next to this carbon atom. How many carbons are directly attached to the starred carbon atom? Everybody make sure everybody's 2, right? Not trying to trick anybody. 2, that will be a 2-degree alkyl halide. For molecule D, again, we're going to locate the halide. In this case, will be chlorine. We're going to identify the chlorine atom. We're going to then find the carbon atom that the chlorine is directly attached to. This is carbon atom. How many carbons are directly attached to that carbon atom? 1 will make it a 1-degree alkyl halide. Oh, I do want to point out, I'm not just trying to go through the degree type because we're not going to use it at some point. We will use the degree type at some point in organic chemistry. Just kind of setting you up so when I ask for the degree type, you know what we're referring to. And again, hopefully not very hard to do. We look at amines. Now for amines, amines can be slightly different. Slightly different. Not too hard as far as different, but actually slightly different. For the amines, we're going to first find the nitrogen atom in the amine. The amine is going to have a carbon-nitrogen bond. A carbon-nitrogen single bond. For the amines, we're going to locate the nitrogen atom. From a little numbers, A, B, C, D. A, B, C, D. We're going to locate the nitrogen atom. We're going to start beside the nitrogen atom. How many carbons are directly attached to nitrogen in that molecule? 2. There will be a 2-degree amine. For molecule B, again, we're going to locate the nitrogen atom. We're going to start next to the nitrogen atom. How many carbons are directly attached to nitrogen? There will be a 4-degree amine, or in biology, what name you call it, we got 4 degrees. Tertiary will be 3, but in biology, y'all even have a name as far as a 4-degree structure. Say it. You're quaternary. Okay, now y'all heard the term before. This is 4-degree or quaternary. So y'all get a little answer. Somebody asks you the answer, you're like, I never heard the term before my entire life. And then so as soon as somebody get an answer, oh yeah, I know exactly what you're talking about. that will do for C. C, again, we're going to locate the nitrogen atom in the molecule. How many carbons are directly attached to nitrogen? 1, that will be a 1 degree of mean. As far as you can put like a particular name for it, 1 degree is also referred to as a primary amine. Next, we'll look at D. Now for D, we're going to find the nitrogen atom. Put a star next to the nitrogen atom. How many carbons are directly attached to nitrogen? That will be a 3 degree or a tertiary amine. Wasn't it fun? Not too hard, right? Again, I may ask you on exam numero dos. Draw a 1 degree amine, or I could ask you exam numero dos. Draw a 3 degree alkyl halide, or I can ask you on exam numero dos. Give me a 0 degree alcohol. And so the 1 0 degree alcohol, which is a carbon atom, and then an OH group attached to it. At this point here, is basically wrap up even that little trace part of stuff here out of chapter 1. Again, it turns out in chapter 1, the naming of the functional groups really came out of chapter. It really started touching in chapter 1, which to me was kind of crazy because they didn't even talk about even organic molecules yet. So I had to kind of actually sneak back into chapter 1 for functional groups. Unfortunately, we're not going to be able to go through each individual chapter and kind of cover it thoroughly as we did problems 1 and 2 because we're going to run out of time. So what I'm going to try to do is actually touch on a couple different parts on the remaining chapters. And to try to make sure we do cover one of the main, there's like two little main concepts we want to make sure we cover in Organic Chem 1. One deals with stereochemistry. As far as the R and S configuration, that's one section of kind of a must for Organic Chem 1. The next section will talk about reaction mechanisms. Reaction mechanism involves SN1, SN2, E1, and E2, which when I say it probably doesn't mean anything. In fact, it's kind of hard, it's kind of confusing me to figure what SN1 and SN2 and stuff actually means. Then also we can talk about as far as reactions of carbon-carbon double bonds. We're not going to actually talk about carbon-carbon double bonds until we first talk about the reaction mechanisms. And the reason I want to talk about reaction mechanisms is because I want to show you a reaction actually that forms a carbon-carbon double bond. Then once we show the formation of carbon-carbon double bond, then we can actually start talking about reactions of carbon-carbon double bonds. So for this first part of it, we're going to mainly just deal with carbon-carbon single bonds. Here's chapter 2. Talk about physical properties of organic molecules. Spread that wrong. Organic compounds. We'll look at boiling point and water solubility. trends and boiling points. Number one, relax. Number two, look for the presence of hydrogen bonding. Next, look for the number of carbon atoms present. Number four, look for branching. Oh snap. It ought to be like a 1A also. No, not 1A, but actually a 2 for us 2 group. Number 2A. Look for N or O without hydrogen attached. Range and decreasing order. We're going to arrange the following molecules in order of decreasing boiling point. Now, I want to point out as far as like the trend and boiling point. First of all, you relax. You're going to look for the presence of hydrogen bonding. Yeah, we also got to touch on hydrogen bonding. What's hydrogen bonding what? There's some people anyway, we just mental little tickle person like that. What is hydrogen bonding like? I don't know what hydrogen bonding is. But I would say hydrogen bonding occurs when a hydrogen directly attached oxygen, nitrogen, or fluorine. Now, what do we know about oxygen, nitrogen, and fluorine, according to GChem?
They're on period 2.
On the periodic table.
On period 2.
Period 2. I mean, they're on the period 2. I also start with an E. Those are the 3 most electronegative atoms on the periodic table that can form a compound. Now, also, one way to memorize this for you is to call it phone. I'm on the phone. Like an F is like a pH phone. It's kind of weird, kind of memorize with elements and stuff on that one. Again, so the first thing you look for hydrogen bonding. The more hydrogen bonding, the higher the boiling point. Now, sometimes you may get an element that may not necessarily have hydrogen bonding. If it has an oxygen, nitrogen, or fluorine molecule, you can actually increase the boiling point because of an oxygen, nitrogen, not can actually hydrogen don't accept, but actually can, if you put an impurity of water, will change the boiling point of it. Number 2, probably not. You're not going to see as much as number 2A as far as like 1, 2. It's really like 2, 3, and 4. But number 3, once you turn the molecule, it has no hydrogen bonding atom present. Next thing you look for is to do the count of carbon atoms. The more carbon atoms you have, the higher the boiling point. For number 3, let's for example, I got an atom that has equal number of carbon atoms. The more branching you get in the molecule, the lower the boiling point. The more branching, the lower the boiling point. So here we're going to look at molecules A, B, C, and D. Yes?
You said what about the branching?
The more branching you have, the lower the boiling point. Yes?
You said
The more carbon atoms, you try to elaborate more on this right here. Chemical train. The more hydrogen bonding, the higher boiling point. Now, at what point the hydrogen bonding even chunks out as far as the number of carbon atoms, especially if it's close and stuff as far as a molecule. You can actually have a molecule, a bunch of hydrogen bonding, and even an atom with a bunch of carbon atoms. The number of hydrogen bonding will beat that out. The more carbon atoms, the higher the boiling point. The more branching, the lower the boiling point. The more branching, the lower the boiling point. The first thing we do is look at our molecules, look at molecules A, B, C, and D. The first thing we'll look for is hydrogen bonding. So we'll look for oxygen, nitrogen, or fluorine. Most of them basically deal with organic molecules, you're only dealing with 2. Oxygen or nitrogen. There's only one molecule in which actually hydrogen is attached to fluorine, that's HF. And HF is not considered to be an organic molecule. So the only molecule we have as far as dealing with hydrogen bonding would be either oxygen or nitrogen directly attached to hydrogen. So we're going to look at molecules A, B, C, and D. The only molecule that has to have a nitrogen or oxygen atom in it would be molecules A and B. So molecule A and B would be our highest boiling points. Now look at molecule A and B. In molecule A, how many atoms can hydrogen bond? In molecule A. Atoms can hydrogen bond in molecule A. How many hydrogen bonding groups do we have in molecule A? How many hydrogen bonding groups do we have in molecule A? One, just the NH group. In molecule B, how many hydrogen bonding groups do we have in that? Two. Everybody, someone looking like, what are you looking at? I'm just looking at the same board y'all looking at. There's only one NH or OH group. It's not like 5 or 6 NH or OH groups in molecule A. There's just one nitrogen, right? It don't take us 20 minutes to realize it's one nitrogen. So like, what are you looking at? Looking at the nitrogen atom. If I look at molecule B, there's only 2 oxygen atoms. It's not like I'm hidden behind something else. There's only 2 of them. It's not going to take me 20 minutes to realize 2. It ain't like, I know what number comes after 1. We know it's 2. So there's 2 groups. So now remember, hydrogen bonding, the more hydrogen bonding, the higher the boiling point. We got molecule A, which has 1 hydrogen bonding group. We have molecule B with 2 hydrogen bonding groups. Which one will be the highest boiling? B. Now let's move on for the decreasing order. We want to go from the highest boiler to the lowest. We go with the highest to lowest. The highest boiling point is going to be B. The second highest will be A. Because those are the 2 that has hydrogen bonding. Now we're looking at C and D. C and D, there's no hydrogen bonding with C and D. So what I'll do for C and D, I'll look at how many carbon atoms make up C. Total number of carbon atoms make up C will be 4. How many carbon make up hydrogen? How many carbon atoms make up molecule D? 4. So then, as far as this group here, the more carbon atoms, the higher the boiling point, since we're equal in number of carbon atoms. That'll help us out. Now we go to subset 3. The more the branching, the lower the boiling point. If I look at molecule C, how many branches do I have? If I look at molecule D, how many branches do I have? 0. Yes.
If it's a situation from C to D, would it still be D, though it has branching, if D has branching? So if so if you took the branch from C and you added to D, even though
you might add it to D to have 5 carbon atoms.
Right, but not adding to, you make it a substituent, like you make it a branch, carbon.
Give me an example what you're talking about for a branch for D, for C. If I took C, this is what I got C here, I got this is D, and you say add something to D.
Right, so just a branch, 2 branches of carbon, or just 1 branch.
Now if I add 2 branches of carbon, my number of carbon atoms is not 4, it's not a tower of 4. The number of carbon atoms will be, the more carbon atoms, the higher the boiling point. This will be with atom with 6 versus carbon with 4. Six carbon atoms want to beat out 4 carbon atoms. You know, so when you start to branch stuff to the molecule, you get the same number of stuff, right? This is when you try to do a direct comparison between I got 4 and I have 4. If you have, if somebody had like 7 at verse 3, regardless of the branching stuff here, 7 is going to end up beating out 3. Because 7 has so many more carbon atoms than 3 would end up having.
So if it was 6 and it was all in one chain, and that was 6, the 6 that branched would be
lower boiling. If I was comparing a 6 versus another 6, this 6 versus 6. The branch chain 6 will be lower than the straight chain 6. Yes.
Okay, can you give another example? You said you had like 20 carbons in your branch. and compare it to that 6 carbon non-branch?
10 going to beat out 6. The number of carbon atoms, before you get to the branching one, the more carbon atoms, the higher the branching. We only looked at 3 because we had a tie. There's 4 and 4. So it's not a number of carbon atoms that was sticking between molecules C and D. C and D are both equal number of carbon atoms. Yes.
So that'll never be 2, that's the same?
I mean, that's what I said. We try to keep it 90% rule one. Now again, when you start doing 90% rule, when you start simplifying it, you can always have this little thing which is like, is it possible to have the exact same? In fact, if you look at for electronegativity, there's actually a couple of atoms on the pure activity that have the same electronegativity values. If you look at hydrogen and phosphorus on the electronegativity table, 2 different atoms, they actually have the same electronegativity values. But I mean, what I'm trying to give you, I'm not trying to get there trying to say how many ways can I trick you about a particular part of it. I'm trying to say if I give you an atom, can you have a general trend about how to rank them as far as highest boiling point to lowest boiling point? I'm not trying to go right. It's like, what kind of way can I end up? If I give you a particular molecule, can I get you to trick you by everything? I'm like, not trying to trick you, but I'm like basically trying to get like a general feel. If you were given 4 molecules, can you then tentatively rank one from the highest boiling point to the lowest boiling point? I'm not looking for a but if I got one over here, what you got like 5 and 4, and I'll make it real tough about letting them figure out which one it is. I'm not trying to do that. In fact, I would not even give you one which is like, if it's like for them, I would give you like a 5 and a 4. Branch 5 and then a straight 4 and see if you know the difference between those two. So again, I'm not interested in trying to trick you about a particular part of it. I want to try to see if you get like a feel about, if I gave different atoms, can I have a feel about what trend it would go in? Not a trend of what can I do to try to trick you. Now I'm going to do some other molecules and stuff here as far as the order. To get kind of credit for doing the board, I use the whole other side. Arrange and increasing. You want to range in increasing order boiling point. Increasing order goes from what to what? From the lowest to the highest. Increasing, so we'll go from the lowest to highest. First one, do is relax. What in the world is he talking? We're talking about crazy stuff, about trying to rank the stuff in order. Relax. First thing I want to do is look for hydrogen bonding. Is there any hydrogen bonding in our 4 examples? No. No. Next thing we'll look for, you could look for NHOH, but it's not present for that molecule. Again, I'll probably not even focus on the NHOH group. As far as single bond groups, much. You probably actually use that more with water soluble than you probably actually do with boiling points. Again, actually probably can try to even get rid of that one. Because again, we try to do like a 90% rule. You're trying to hopefully cut away a lot of the little excess fat about trying to memorize the stuff. Because when you try to get the stuff together on like an exam, The less you have, the better you have as far as trying to simplify data. So the next thing we'll look for the number of carbon atoms present. In molecule A, how many carbon atoms do we have present? So we have 7. B, how many carbon atoms present? 3. C, how many carbon atoms present? And in D, how many carbon atoms present? The greater the number of carbon atoms, the higher the boiling point. The one with the highest boiling point would be A. The one with the lowest boiling point would be D. All right. Not D. The lowest boiling point would be B. 3B has 3 carbon atoms.
I thought you said the lower, the higher the branches, the lower.
We get to, so you go to the next rule. We're doing right here. Look at the number of carbon atoms present. 7, 3, 5, and 5. 5 carbon atoms are going to beat out 3 carbon atoms. So the lowest going to be, the highest going to be A, lowest will be B. Now the question comes up, which the between C and D, which one will be the higher between C and D? C will be higher. D. Range will be B, D, C, A. Now again, I can always take number B and make it just 2 carbon atoms. But again, I'm trying to point over here. When you get to the order, it's the number of carbon atoms first. Don't stop here for looking at the number of carbon atoms. Oh, forget about the rest of the stuff. We just jump to the number of branches. You gotta go in the order. Number of carbon atoms is going to beat out branching one. So again, if I just got 3 carbon atoms, each one of those molecules got at least 3 carbon atoms in the molecule. Now again, it would actually decrease, but not going to decrease enough to make up to the count for the fact of you having 2 more extra carbon atoms. Now again, what I also can do over here, I can actually put it so that there's a big discrepancy between the little individual numbers and stuff for those. So if basically if it's 5, I can make between 1 being 7 and B could have been 2. Arrange in decreasing order of boiling point. First thing we look for is hydrogen bond. Notice no hydrogen bond is present. Next thing I look for is number of carbon atoms. How many carbon atoms present in molecule A? 5. How many present in molecule B? 5. How many present in molecule C? 1. How many present in molecule D? 5. We want to go from decreasing order. We want to go to the highest to the lowest. Okay, we're just thinking between any one so far. We can get the lowest. The lowest is going to be C. So we're going to put a note highest to lowest. Now we have a tie, A, B, and D. So everybody like to say like about the little branching. Now we get to the branching. Molecule A, how many branches does it have?
0.
0. Molecule B, how many branches? 2. Molecule D, how many branches? 1. The one with the highest boiling point would be A. Second highest boiling point, D. And the lowest from that set would be B. So it'll be A, B, D, C. A, D, B, C. A, D, B, C. A, D, B, C. What's the front end? Somebody fill in there as far as doing the arrangement in boiling points. Next, we're going to talk about arranging in solubility. Determine the trend in water solubility. And water solubility. Number 1, you're going to relax. Number 2, look for hydrogen bonding. Number 3, because basically try to determine that one end up shortening it or make it as simple as possible. But by making it simple, you can end up losing some little nuance as far as doing that one. We had to lose some nuance and try to hopefully keep it simple. When I did one like that 2B from 2A last time, you can probably take that one out just to make it even more simple. But again, when you start trying to memorize the stuff, the simpler the better. You will lose some little details as far as like some of the simple ones, but when you try to start arranging some of the stuff for here, you don't want to get a whole bunch of different rules. You don't have 8,000 different rules to try to memorize when you try to do something. So look for hydrogen bonding. Number 3. The more carbon atoms, the less soluble, the less water soluble. The more carbon atoms, the less water soluble.
Is that all the trend?
We also could put up one little trend, could have been if you have an oxygen or hydrogen present. Oxygen and hydrogen present will make it more water soluble than something that does not have none. Not an oxygen or nitrogen present will also make it more water soluble.
Or nitrogen?
Oxygen and nitrogen. Because those acts in hydrogen accept, hydrogen donate.
Make it more soluble?
Makes it more water soluble. Yes, we could make a third one here. Make a fourth one. Take out. Change number 3. 3.
The order of 3 and 4 matters just like the other one?
Yeah, because basically say, first thing, the reason I look for the first one, hydrogen bond, is because hydrogen bonding makes it more like water. Water undergoes hydrogen bonding. Remember like back in G-Chem, Like dissolves like. So once you get a molecule that's more like water, it wants to dissolve in water better. The reason why the carbon atom is not dissolving in water because those are less like water. Carbon atoms would be non-polar. Water is going to be polar. So if you make a molecule more polar, you also make it more water soluble. You make the molecule less polar, you make it less water soluble because it's less alike. Now, when you're looking at molecules A, B, C, or D, the first thing we'll look for is hydrogen bonding. Which atom can hydrogen bond? B and C. I got B and C. Now, what's the difference between, got two B's. B and C. What's the difference between B and C? One has one hydrogen bonding group, the other one has two hydrogen bonding groups. Two hydrogen bonding groups are more like water than one hydrogen bonding group. So the one is going to be the,
What are we doing?
try to determine the solubility. We haven't set the order. We actually haven't set the order yet. I mean, we haven't set which we will increase or decrease it. But again, if I look at it, the one with the more hydrogen bonding would be the one to be more soluble. If, then for example, you had like an oxygen atom in a molecule, which is not one of these things for here. An oxygen atom or a nitrogen atom in the molecule would make it more water soluble than one that didn't have an oxygen atom in it. Again, it's not one of the examples shown on the board, but I can show you one with an example. That should be consistent with the example you may see in the textbook. Now, once you get rid of all the hydrogen bonding, then you're going to look as far as, and also there's no NH, there's no nitrogen or nitrogen or oxygen present. Then you're going to look for the number of carbon atoms present. The more carbon atoms present, the less water-like it becomes, less like water becomes. When it becomes less water-like, it becomes less water-soluble. So now we get between A and D. Look at A and D. A has 2 carbon atoms, D has 6 carbon atoms. The more carbon atoms you have, the less water soluble you will be. So D will be the least water soluble, then you follow by A, B, and the most water soluble would be C.
You said do D.
D will be the least, then A, B, and the most water soluble will be C. Because C has the most, C is most water-like, has the most OH groups, most polar-like.
Okay, so when we did, the last time we did this, you said look at the number of carbons before the branches, right?
Remember looking at water solubility.
Okay, yeah.
Remember, the more carbon atoms you got, the less water soluble it will be.
That's not what I'm asking. If, okay, so 3 was for the other one. The boiling point was good for the number of carbons, and then if you got one that's tied in the branches. So I was asking for this one, you said D would be the least.
Yes.
But 4 is last, so I'm saying if I look at the non-hydrogen bonding, which would be between B and C, why wouldn't you use one of those first like you did the other one? You see what I'm saying?
Let me see in the order. When I did the order, we looked at hydrogen bonding first.
Yeah.
What we do in the last one? What came next?
You said what?
What do we look at next?
Then we look at the number of carbons.
So we got number of carbon atoms. We got 6 versus 2.
Right. But last time we did that, we used the first 6 that we went through, like in my notes, when I was like, the more branches, then the lower the boiling point.
Yes.
You said count the carbons first and use do between the carbon numbers, use those first. So I'm saying in this one, why didn't I use when you said that the more oxygen and hydrogen is higher? Why didn't
Make it more. You want to make it more like water. HOH. Hydrogen bonding, hydrogen bonding. Carbon atom is not going to make it more water-like.
Okay.
So remember, you want to look for the more water solubility. Why would you look for carbon atoms, you want the thing to be more water soluble. And if you want it to be less water soluble, then you start focusing on carbon atoms. Because when the OH groups, because in this molecule, you want to make it more like water. Water got this little OH group, hydrogen bonding, hydrogen bonding. This molecule has hydrogen bonding. This molecule also has hydrogen bonding, it just has more hydrogen bonding. This molecule doesn't even get anything like water, because water is a polar molecule to hydrogen bond. These are not polar molecules to hydrogen bond. Both are going to be insoluble in water. This just happens to be less, they have to be like more insoluble than this right here, because it has more carbon atoms. The more carbon atoms you get, the more unlike water you get.
So there's nothing wrong with looking at a problem like this and automatically assuming that the ones with OH is more soluble.
Yes, as far as, remember the question asked for water solubility.
Right.
Now again, if somebody asks you which one is the least water soluble, you got to remember also you got to pay attention to what the question saying too. Okay. But sometimes you may get the rules and stuff here, which is like, yeah, the same water soluble rules, same water solubility rules. But if the question asks you which one is the least water soluble, then you got to remember the same one. You got to switch around, because they asked you not for the one more water soluble, but for the one that's the least water soluble.
I would look for basically the ones without the hydrogen and oxygen.
Yes. That's what I say. Sometimes you got the concepts together, but sometimes you may take the question and twist the question around and throw it completely off. Now I'm going to do a molecule which actually has an oxygen atom attached to it, oxygen nitrogen attached to it. Arranging increasing order. Of water solubility. Now you're probably saying 4. 4 is just not as much fun as 5. So you do our relaxation. Let's get this thing all checked up. Now the first thing you look for water solubility. After you relax, the first thing you look for is what?
Hydrogen bonding.
Hydrogen bonding. Which atom has go hydrogen bonding?
B and E.
B and E. Now for this question here, you want to go from increasing order. I want to go from the least water soluble to the most water soluble. So I'm going to look between B and E. The one that will be the most water soluble will be E. Followed by B. If you want to find out which one is the least water soluble, we got A, C, and D. Which one's the least water soluble?
B.
Which one? We just did B. I already do it. If I already did B and D, right?
D.
Yes. How would D be the least one if you just said one of the most water soluble?
The less carbons.
I'm just saying, but somebody mentioned B. I'm like, you put the star beside B and D already.
So C.
So when we got A and we said B and D would be the most.
B and D.
It can't gonna be like it can't be 1 second be the most, and then the next time we ask it gonna be the least. But we start B and D as being B and E as being the most water soluble. So now we're trying to figure out between that set we got remaining which one would be the least.
It would be C. D. The less carbon you have.
Remember, water solubility. I want to go from the least water soluble to the most water soluble.
Okay.
To be the least water soluble, we need to make it the less like water. The one to be less like water would be
D.
D. I just want to say, I keep saying, I keep running, I keep hearing C pop up too. C. I want to make sure that everybody on the same page. We can't go like head in class saying like C. I heard somebody say C. I guess the answer will be C. The answer would be D. D has the greatest number of carbon atoms. Now we got between A and C. How's it between A and C?
C would be the least and the highest is A.
C would be the next. Now then between A and C, if you look at A and look at C, both got the same number of carbon atoms. The thing is that A has an oxygen atom attached to it. A does not have a hydrogen bond and oxygen atom because in order to hydrogen bond, oxygen must be directly attached, hydrogen must be directly attached to oxygen, nitrogen, or fluorine. In that molecule, there's no hydrogen atom directly attached to oxygen in molecule A. But it does make it more water soluble. So the one's going to be, it will be C as being next, and then you have A. And this also be more consistent with the one as far as the book gave you, which is in the chapter 2. And chapter 2 talks about the properties of boiling points and water solubilities. Remember, for our little rule 1, for order, I look for hydrogen bonding. Hydrogen bonding took care of B and E. The next thing I look for is what? Non-hydrogen, oxygen, or nitrogen. I'm looking for oxygen, nitrogen present in my rest of the molecule. This one has an oxygen present. None of them have an oxygen present. No oxygen present. An oxygen present is going to be stronger than one that has no oxygen atom present in the molecule. Oxygen, nitrogen. Now, the oxygen atom is not going to be able to what is called hydrogen donate and accept. It can only hydrogen accept if it has another water molecule around it. But it then goes back to the concept about hydrogen bonding from GChem. If it was a regular year, we could spend more time about explaining that little GChem rule 1. Unfortunately, during summertime, we ain't got so many days of actual meeting. But we went into more detail when I would stop our office hours after this class. We give more details behind that one. So again, you're going to have one exam, numero dos. Ask you about boiling point trends and also ask you about water solubility. Boiling point trends and water solubility both come out of chapter 2. So we're going to go ahead and look back at that come out of chapter 2. We're actually going to skip chapter 3 to go into chapter 4. Chapter 4 talks about the energy conformations of ethane, propane, butane. Then also talk about the energy conformations of cyclic rings. So on next Tuesday, we'll have chapters 2 and 4. Yes.
Tomorrow is chapter 2,
All we covered in chapter 2 was just the solubility stuff. Then we're going to chapter Started already?
Yeah.
Yeah, chapter 4 we can start today. I was like, 20. This is chapter 4. Now, again, I'm not going to be able to cover like how we end up going through more detail with chapters 1 and 2. And we do the same detail between that we did in chapters 1 and 2 through the whole entire chapter. We're not going to cover very much. But again, I'm not trying to get into every little single detail in every individual chapter. This is chapter 4. And we'll look at energy confirmation. We're going to look at energy confirmation of ethane, propane, butane. We're also going to look at cyclohexane. And we're going to have a new drawing in tape. We're going to use a new drawing known as the Newman Projection. First of all, we'll do ethane. Ethane will be 2 carbon atoms. At means 2. A and E refers to the fact that it's a single bond. We have 2 carbon atoms single bonded. And we're going to do, we call this carbon number 1 and carbon number 2. You can call any one of those carbon atoms being carbon number 1 and carbon number 2. We're going to take ethane and we're going to represent it using the Newman projection. We got a big circle and a dot. Dot represents carbon 1. The big circle represents carbon number 2. We have a dot and a circle. What is attached to carbon number 1? 3 hydrogens. Attached to carbon number 1 is going to be 1, 2, 3 hydrogens. The second one represents the big carbon. It's kind of like looking right like they got 2 carbon atoms standing right behind each other. And you basically look for here, for example, like we're standing right together, and you would look kind of like through the back of someone's head. You always probably you'll see like a little small part of me because I'm basically being clipped by someone else. This kind of like a little dot, and then a little big circle, kind of like a little big, the ones you're clipped in the back. As far as which one you call carbon number 1 or carbon number 2, that's really up to you. Now, what is attached to carbon number 2? 3 hydrogen, like what's attached to the first one. I got an H here, an H here, and an H there. Now, I would say maybe not a bad idea. We had like a little chemical model kit. I can show you a little chemical model kit, and I can show you a little rotation one. And we try to do is have one of those on tomorrow's class. What are you going to do for the energy diagram? You're going to end up having like a little energy curve. You have energy, rotation. You're going to rotate from 0 to 60. To 120, to 180, 240, 300, 360. What's the significance of 0 to 60? 0 to 360?
Circle.
Made a complete circle. All we just remember a complete circle. We're going to end up doing for this molecule, we're going to keep one of these two carbon atoms set. It really both of them spin at the same time. But again, when you spin them both at the same time, it's kind of hard to confuse and try to keep track of each one thing. What we're going to do, we're going to take one of our carbon atoms, we're going to lock it in place. And we're just going to rotate the other carbon atom on a complete circle. Let me set the back. What I'm going to do, I'm going to try to set my, basically going to keep the black back one when they have the hydrogen atom at the top and one to the side. I'm going to lock that in place. And what I'm going to try to do is rotate the top carbon atom, the front carbon atom. This top, the back one will be still locked. I'm going to rotate on the top one, the first one, all around 360 degrees. Where I'm putting this right here together, I'm going to put it so they got one hydrogen blocking the second hydrogen. Like one hydrogen behind another one. Kind of call it eclipse, but like the moon blocks out the sun. We're going to have one hydrogen atom blocking another hydrogen atom. Just like the moon blocking out the sun, the term of that arrangement is called an eclipse arrangement. This is going to be eclipse. As far as angle, we're going to call this 0 degree. 0 degree one is arbitrary way you start. I just want to have like a starting point. I like to start point when the basic start is straight at the top. Then we kind of quickly go around one complete circle. Then we got my second group that's locked, and I'm going to rotate the first carbon atom. All I'm going to do is rotate 360. As I rotate it, what's the bond angle between this hydrogen and that, between the two hydrogen atoms in the molecule? Looking at it. What's the bond angle? 120. Now, to get 120, what you do is going to move it 60 degrees to get it in the middle. Once I move this 60 degrees, this moves 60 degrees, and that moves 60 degrees. Now, what's the significance of 60 degrees? 60 degrees is the furthest you can get those two hydrogen atoms apart from each other. Now, as far as energy goes, for example, like you have like two little elementary school kids, and they just can't stand each other. You think it's going to be high energy or low energy? Remember, the more rage, more excited you get and stuff, the mad you get, are you going to be low energy being calm, or you going to be raised up energy being upset? If you got two people who don't like each other and they all in each other's face, you be high energy. Now, what if I take those little two people and I then separate them from each other? And 160 degrees. Keep my back one locked in place. When I rotate it 60 degrees, this is here, here, and there. At 60 degrees, I separate the two people who don't like each other. 60 degrees is further apart. I can get those two together. Get the two apart from each other. If you got two people who don't like each other, what happens when you start separating two people together over time? Eventually, over time, it's about calm down. I get more relaxed. So basically, I go from being high energy to low energy. So I go from high, then I go down low. Now, when you rotate me another 6 degrees, what happens? Again, I'm going to lock that one carbon atom, lock it in place. And I'm going to take this front one and rotate it another 60 degrees. That rotates 60 degrees, and this rotates 60 degrees. That's what then put these groups eclipse to each other. So now I found another little young person stuff here, little kid stuff here I don't like either. All in my space, and then drink my little juicy box up. That person drunk my juicy box up. And that's my favorite juicy box. You think I'm gonna be mad or not? Will it be high energy or low energy? I'm gonna be all high energy. You took my juicy box, my favorite juicy box. You're not my free no more. So when I rotate another 60 degrees, I'm gonna go back to high energy. So now I went from 60 to another 60 degrees. This made it 120. I rotate another 60 degrees. H, H, H. I rotate another 60. This comes here. This goes up there. And that group goes there. So all I got are two arrangements. High energy, low energy. High energy, low energy. I'm going to do this curve all the way through. High energy, low energy. High energy, low energy. High energy, low energy. High energy. Goes back and forth. What kind of wave in math is that? Because it's like either sine or cosine. I'm not sure which one it was. Okay, so it's cosine. So you got like a cosine wave. So you're going to tap a little math stuff in there. So you got a little cosine wave. All you got is basically two arrangements. When you get it back behind each other, it's called staggered. When they're apart from each other, that's called, in an eclipse, when they're back behind each other, other one called staggered. Some people also refer to it as being gouge. If you were to hear like the term gouge, all gouge referred to is basically like another name for staggered. They all say the same thing, just kind of like a different word to say the same thing. But you're going to arrange, you got either staggered, keep saying staggered, eclipse, staggered, eclipse, staggered, eclipse, staggered, eclipse, staggered. Yes?
So like this number 2, when you have like the chart and the eclipse staggered diagram and model.
In fact, we're going to get to a point in which we're going to already know there's only two diagrams. All I'm going to have two diagrams. Staggered and eclipse. Even when you get up to 4 carbon atom groups, there'll only be 2. But actually, 4 are going to end up giving like 4 different structures. We're going to talk about how to get those 4 different structures. They're going to be so fixed over here. Once we lock one group and stuff in together, we're going to have 2 arrangements. Either staggered or eclipse. They're going to look all super crazy stuff over here. Part of it is super crazy. But we'll hopefully try to see, can you see what we actually do? Yes?
So the first staggered diagram, is it supposed to be double-headed arrow?
No, I want to show it like 60-degree angle.
Okay.
I was trying to incorporate like this angle here, 60 degrees. It really, like I said, not like a double-headed one, but actually rotated. But it's been indicated the difference between those be 60 degrees. It turns out once you get 60, for example, what if I do 70 degrees? Once you get 70 degrees, yes, the distance between this carbon atom and that carbon atom would increase. But then the distance between those two decreases. So only at 60 degrees are you get it exactly with both the further apart from each of the two groups, each of the two hydrogen atoms. Now when you do the propane molecule, for the propane, first I'm going to do an active draw the structure. Pro is going to be how many carbon atoms? Mama eats peanut butter. 3. You got 3. 1, 2, 3. Put a hydrogen atom on a molecule. Now we're going to convert this for here into a Newman projection. Newman projection only involves 2 carbon atoms, carbon 1 and carbon 2. Which carbon you want to call carbon 1, which carbon you want to call carbon 2? Now because our numbers, 1 got to be next to 2. You can't have like 1 and then like 1, 2. It ain't like a little long drawn out count. The next one will be number 2. It can't be like 1, then I'm going to call the next one being 2. So you got 1 next to 2, no matter which one you call 1, which one you call number 2. So what you call this will be number 1. And that will be number 2. So we give our little circle. And our dot. I'm going to lock one group. What's going to be attached to carbon number 1? 3 hydrogens. H, H, and H. Carbon number 2, I'll put it eclipse. I got a bond here, a bond there, and a bond there. What atoms attached to carbon number 2? 2 hydrogens and the whole group. 2 hydrogens and a CH3. That's what attached to carbon number 2. Attached to carbon number 2. I'm not going back to number 1, but like I'm not count myself here. I got one already. Attached here will be a hydrogen, and this whole group is a CH3. I'll put my CH3 group at the top. In fact, it really doesn't matter if you set it at the top or at some other place. What I like to do is kind of set my C3 group at the top, and I'm calling that angle 0. This for here is kind of like a small person being a hydrogen and a big person being a C3 group. Now those two people don't like each other. So now you think it's going to be higher energy than 2 little kids or lower energy than 2 little kids. Higher. We don't know. We're not sure exactly how much higher, but it should be higher energy than just 2 little kids. In this arrangement, we're only going to have 2 arrangements. It's either going to be eclipse or staggered. Move 6 degrees. Again, I'm going to lock one carbon atom in place. Here, I'm locking my back carbon atom. Whatever attachment to my back carbon atom, I'm keeping that in the same place. My back carbon atom has a CH3 that I keep in place, an H that I keep over here, and an H that I keep over here. What I did, I moved my little H group 60 degrees. The first H moves 60. This H moves 60 degrees, and this other H moves 6 degrees. So we have H, H, and H. Here you got 2 arrangements, eclipse and staggered. Now as you move those little big person and small person away from each other, they're going to be lower energy, but not as low as separating out 2 small people. The reason why I have it for 2 small people, because this group here is actually bigger, it's going to be a little bit closer, because for the small person, a small person take up less amount of room. Big person will take up more room. Because I'm taking up more room, you're actually not as far away from me as you were if there were 2 small people. So your energy will become lower, but not as low as if there were 2 small people. So it's kind of like having this one, in which, I go down, but not quite as low. I go up a little bit higher, down, up, down, up. Not as much fun because basically all I'm doing is basically the same cosine wave I did with ethane, except it's just slightly higher. Now we're not stating how much higher for the energy difference for like how much higher the energy is. We just basically trying to get like a little feel about how the energy stuff will end up going. How are we feeling so far? But again, like I said, all we have is two structures. Eclipse or stagger. Even in the next part, we're only deal with two structures. Eclipse and stagger.
Yes. The CH3 is kind of like the driving force to whereas before you only have the heating.
I mean, for hydrogen, we just go like hydrogen kind of do like people type arrangement.
But
this is a big person, small person.
I mean, I understand that.
Mm-hmm.
I was looking more towards like the force and electronegativity, like the reason why it's driving such high energy.
I mean, so we have not said how much higher this is.
Right.
We're not trying to quantify how much higher it is. We just know it should be a little bit higher. How much higher? We're not actually stating how much higher it will be. There is a calculation you actually calculate the energy difference type one, but again, we're not trying to get into all of it took apart. I mean, we only got 4 weeks. But except for, what's what we end up doing? Again, we're trying to do, we're locking one group. And all we're doing is rotating one of them. But again, notice here, we only got 2 structures that's either eclipsed or staggered. Even when we start doing the one doing butane, we're only going to have 2 structures. Eclipse and staggered. But we are going to have 4 different names for our energy diagram things. We're going to start going back with some more of that math terminology. I'll get my little energy thing for a second. We have butane, 1, 2, 3, 4. We're going to convert butane into a Newman projection. Newman projection abbreviates 2 atoms as being a dot and a big circle. In this molecule, you try to come with which atoms it'll pick. And you want to pick the 2 carbon atoms that will make this molecule as symmetrical as possible. The atoms that make this molecule as symmetrical as possible will be using the middle 2 carbon atoms. In the middle 2 carbon atoms, that means that both carbon number 1, which will be a dot, and carbon number 2, which is a big circle, both of them will get a CH3 group. So I mean, we treat both of them exactly equal so that both are split exactly equal the same way. You couldn't do the same thing with propane because propane got an odd number. 1 carbon atom has to have a CH3 group, the other one won't have one. In this arrangement, we're going to call this carbon number 1 and carbon number 2. We're going to have a big circle, a dot. We're going to tap the back, we'll lock it in place. Back we got CH3, an H, and an H. That's the back carbon atom we've locked in place. What is attached to our front carbon atom? To the first carbon atom, we got 2 hydrogens and a CH3. Put an H, and have a C3. If you want to put the little group of stuff for a different location, it's not that big of a deal. I like to put a little 2 hydrogen, 2 C3 groups together because that would be my position number 1. Yes.
So the big one, is that carbon 1? Like the big one?
The circle is, this dot is carbon number 1. Dot is carbon number 1. This is carbon number 1. What is attached to carbon number 1?
2 hydrogens and CH3.
Hydrogen, hydrogen, CH3. Now we're looking at carbon number 2. Carbon number 2 is shown in my big circle. What is attached to the carbon number 2 to the big circle? A hydrogen, hydrogen, and a CH3. Remember, this is 1. All I'm doing is looking at what I saw on the board. I'm not trying to cover any different atoms what we see on the board. If we look at atom 1, I'm not counting number 2. What is attached to carbon number 1? Carbon number 1 is a dot. Attached to carbon number 1 is a hydrogen. There's 2 hydrogens. What else attached to carbon number 1? You sound like you're not believing what you're seeing.
I didn't say it.
But you're like, CH3, like this. When somebody say they sure about something, they want to like, what's the right answer? Go left or right? Left. I'm like, when you quiet like that, you mean like, give me something. Tell me like, go like, did you say go? Then you go the wrong direction. I told you go left. Like you must not have said. You was awful quiet saying it. Go left. If you right, then yeah, I say go left. But again, I won't tell what you're going to see. What I will do is try to say what you actually see right here. So we got, can you see the H, H, and CH3? Attached to the back will be an H, H, and a CH3. What I'm doing is put my group together so I'm just establishing position 0. As far as you want to change a different